Hey everybody, it's Chill here. Welcome back to Hardware 3D. We've got our quick and dirty draw test triangle function here. And now we're just going to play with it for a little while. We're going to try some stuff. We're going to break some stuff. We're going to see what sticks to the wall. So, first of all, we're drawing a single triangle. Let's try and draw two triangles. So to add another triangle, it's super simple. Just add 3 more vertices to our array of vertices. Now, see if you can visualize what kind of triangle this is going to make just by looking at the coordinates. Little exercise for you, and let's see if your prediction was correct. And we get nothing. So, was your prediction correct? If it was, you just passed the trick question. Because this is the same, basically the same as in 3D fundamentals. Triangles, by default, the pipeline will do backface culling, meaning it will look at the winding of the triangle and it will cull triangles that don't have the correct winding. So if we visualize this one, we can see that the winding is clockwise. It's going here to here to here. But this one is going counterclockwise. So all we got to do to fix it is just interpose 2 of the vertices. And now we should see 2 triangles. And we do see 2 triangles. So was your prediction correct? Who knows? Let's move on. So you got 2 triangles. And one good thing to notice here is because we made our code very reactive, it was very simple. We just added some more vertices and it just worked. What I mean by reactive is stuff like using size of vertices here instead of hard coding the byte count, or using std size on vertices instead of hard coding the element count. So that's very nice, right? All right, now let's try something completely different. So we'll go back to our normal triangle. Let's say we want to draw lines instead of drawing a triangle. So all we got to do for that is a very simple change. Incredibly simple. All we got to do is change the primitive topology. So instead of a triangle list, let's try a line list. And what do you expect to happen here? Make a prediction. See what you think is going to happen. So we run this and we get a single line here. Is that what you predicted? You might have predicted, well, we'd get another triangle, but it would be drawn with a thin line instead of being filled. But think about it. What is a line list? Well, every line has 2 vertices, right? So first of all, you would expect a line list to have a multiple of 2 vertices in the buffer. We've got 3 here. So we're only going to get 1 line here. This one is only half a line. It's not enough to draw a line. So what would we have to do if we wanted to draw a triangle with lines? Well, we've got from the first vertex to the second vertex, and then we got to go from the second vertex to the third vertex. That's these 2. And then we got to go from the third vertex back to the first vertex. And this should draw us a line. Note that there is no such thing as winding with thin lines. Doesn't matter what order you put them in. There you go. You've got your triangle. It's being drawn with thin lines. Very simple, right? Now this is kind of redundant here. We're doubling up on our vertices quite a lot. So there's another kind of primitive, and it is supported for lines and for triangles, if I can frickin' find it. And it's called a strip. So strip configuration, line strip. And if we do that, now it'll interpret it as adjacent vertices will have a line between them. So there'll be a line between this one and this one, this one and this one, this one and this one. So we don't need to double up on our vertices here. We just need to go from vertex 1 to vertex 2 to vertex 3 back to vertex 1. You need to double that one up here because it doesn't wrap around. It's not a closed line list, it's an open list. So you've got to double up on one of the vertices if you want it to close up. And there you go. So strip is going to be more efficient in general for your vertices. But for triangles, we're generally going to use just lists because they're more flexible, and we're going to index those lists. And I'll show you that a little bit in the later of this video. In the later of this video. Okay, let's move on. All right, so this plain white triangle, it's kind of boring. Let's spice it up a little bit. We're going to give each vertex its own color, and then we're going to let the pipeline blend those colors when it rasterizes the triangle. So this is we're gonna have to do a little bit of shader work on this bad boy. So first of all, I mean, you could start wherever the heck you want to start. But let's start with the definition of the input layout. So now each vertex is going to need not only its position, but also its color. And here we go. So let's give another element here, and we're going to call this element color. And we can specify different formats for this. Let's start with just a 3-part floating point element. So that's RG, and then if I just go B32, it should just work. Now the offset of this into the structure is going to be 8 bytes, because there's 2 floating point values that precede the color. So that means we are 8 bytes deep into this structure by the time we reach the color element. And the rest of this is just going to stay the same. And the rest of this stays the same. And because we're using std size, that just automatically adjusts here. So everything should be good. Now, what we want to do next is look at our, well, we can adjust our buffer now. First, let's adjust our actual structure defined in C++. So now we need stuff for the color. So we'll define RGB as floating point values. And then for our vertices, we also got to jam in our RGB values in here. And that'll look something like this. I give each of the vertices a separate channel that's set to 1. 1 is going to be full. 0 is going to be nothing in that channel. So just keep that in mind. And I believe that's it for here. Now we've just got to adjust our shaders. So the vertex shader, now it is going to be taking in 2 kinds of inputs. It is going to be taking in our good old friend, the position. But it's also going to take in a float 3. That's wrong. Float 3 color. And the semantic for that is color. It's got to match the semantic that I gave in the input layout. And now we're returning. We got to output not only the position, but we also have to output the color of that vertex. So we got to output 2 things. And the easy way to do that is with a struct. You can define structs in HLSL. So we're going to call this one VS out, and it's going to have 2 components. It's going to have the position as a 4-element vector, and it's going to have color as a 3-element vector, both floating point. And now we're going to return, instead of returning float 4, we return VS out. We don't put the semantic on there. Semantic is now inside the structure. And so now we have to actually create the structure and then output it. And that's going to look something like this. We just now put that color into the structure. We pass the color through as is into the transformed vertex. And that is going to be interpolated by the rasterizer, the color is, and is going to be presented to the pixel shader as an input. So now in the pixel shader, instead of taking nothing, we can finally take something. Float 3 color. And the semantic on that's going to match the output of the vertex shader. So that's color. And now, instead of returning just a constant color, we return the color attribute that has been interpolated by the rasterizer. We just return that as is. Now, it looks like I screwed up a little bit here, float 3 to float 4. So your output color has to be a float 4. So we've got to expand this float 3 color into a 4 channel. We can do it like this, constructing a float 4 from a float 3 plus the 4th channel value. Now, when we run this, we get a big fat error. So what's this bullshit? Well, have fun trying to decode this one. Vertex shader, pixel shader linkage error, signatures between stages incompatible, semantic colors defined for mismatched hardware registers between the output stage and the input stage. What could be the problem? Well, here we're inputting color. Here we're outputting color. What happened? Well, here's the thing. We're outputting a structure, and it's got 2 elements to it. So the first element is what the linker is going to try to match to the first element of the input here. Only we're not taking the first one, we're taking the second one. And you might think, well, it's got this semantic on it. It'll be able to figure out which one matches to which, but it doesn't. It'll use the semantic to check and give you an error, but you've got to match the order. So what you can do, very simply, put the color first. Now, this one is only taking 1 element. It'll try to take the color will match, and it'll work. And there you go. You've got a pretty little triangle. Beautiful. All the colors of the rainbow. Not really, but yeah, it's good enough, right? Now, one thing you might be wondering here is, do we really need floating point values to specify the colors in here? I mean, that seems like a big waste of space, right? We could specify each channel with just a byte, and that would be plenty. And the answer is yes, we have freedom. We can choose to specify these with a byte instead. But I think you'll appreciate that if we do that, we've got to make a few other changes to our pipeline. First of all, our input layout is definitely going to have to change here because now it's not RGB 32-bit floats. It's going to be something else. So what is that going to be? Well, to figure that out, we've got to pour through the DXGI format enumeration and see if we can find something that matches. So here we have a whole bunch of guys that are RGB 8. Can we find one that's just RGB 8? I can't seem to find one that's just RGB, but that's good anyways. We don't really want a 3-byte element. That would be bad for padding and stuff. So we're going to use RGBA8. Now, there's a whole bunch of them in here. What do we want? Well, we want to make it an integer, right? So let's try uint, unsigned integer. That seems like it's exactly what we want. Wink, wink. So we change this to RGBA8, all 8s, and I guess we'll put an A in here to make that match up. Beautiful. And then we've got to change this input stuff here. All right, so this matches this, and that's our input layout. Let's see what we get. Well, we get a big black triangle. That's not what we wanted, was it? Something must be wrong. We're still missing something. Here's the thing. So when you pass your data in and it goes into the vertex shader here, our vertex shader is specifying it as a float 3, a floating point number. We're passing in integer values. Now, Direct3D and all the stuffs, they will convert your input into the type specified in your shader here. But there are rules for how it's converted, and you can control that. And that's what these little guys at the end are all about. So, uint just converts it as its exact value, integer value. But here's a good one. unorm will normalize it to the full range of the input type. So, for example, if you input 255, when it converts that to float, that will be 1.0. And when you input 0, that will be 0 float. And when you input 128, that will be 0.5, etc., etc. And that's what we want, because we want our colors to be in the range of 0 and 1 floating point, not in the range of 0 to 255, which is, I believe, what we would get with this one, although I haven't actually confirmed it. We'll see. Anyways, the important thing is that we have to change our specification for that input layout from uint to unorm. And then it'll be normalized when it's input into the shader. And then we get our colors. Only this time, the vertex data has been specified with integer chars instead of with floating point values. And notice that this is a 4-element color. And what the vertex shader is taking is 3 elements, and it doesn't cause any problems. It just ignores that last element, and everything still works properly. Now, on the C++ side, we've just been declaring this vertex as a flat structure. But you don't have to do that. You can give it some more organization if you like. So let's make it a structure of structures. So here we declare an anonymous structure, and we instantiate it as pause in the vertex, and another anonymous structure as color. And we could use this if we liked. So let's use this to access one of the vertices. So we go vertex 0.color dot, let's see, green is equal to 255. That should change that one to yellow now. And we can just run that and it'll work. There you go. We've got yellow up here now. You might be surprised. You might say, well, Chili, you changed the structure of your vertex. Why didn't you have to change the input layout? But of course, these bytes still have the same order in the structure. Just because you've added some extra structures in here doesn't change anything about the actual data in here. It's still a float followed by a float followed by a car. We just made it a little more organized, that's all. Now let's add 3 more triangles here to make a hexagon. Alright, so after an annoying bout of data entry, I've got my 4 triangles here, and that is going to make me a retarded hexagon. Now the first thing you're going to notice about this, well, maybe not the first thing, but one thing you'll notice is there is a lot of waste here. How many actual vertices do we have? We have 1, 2, 3, 4, 5, 6 vertices. But how many vertices do we have to specify in this data structure? We've got to specify 12. Now, those of you from 3D fundamentals will probably already know the answer to this problem, and that is you use index drawing. So instead of specifying and repeating yourself with all these vertices, you only define the vertices once, and then you use a set of indexes to select them to draw the triangles. So how do we do that with Direct3D? Well, first we're going to remove all the redundant vertices. Now, we need an index buffer. Well, let's take a look here. Let's not get ahead of ourselves. So in order to draw with indexes, we got to use a different draw function. We use draw index. And that is going to take different parameters. It's going to take the count of indexes, the index start location, and then the base vertex location. So now we need, first of all, we gotta ask ourselves, well, how does it know what indexes to use? And the same as with our good old friend, the vertex buffer, you've got to bind that to the pipeline. So create index buffer. Now, if memory serves correctly, indices are 16-bit by default. So I guess that should be an unsigned short there. Don't want negative indices. And now we need to specify indices for each triangle that we want to draw. And we're going to index into this vertex buffer. And basically just by eyeballing it and trying to visualize in my mind, I came up with these indices. Probably some of them are messed up, but we'll figure that out when we get there. So now we have our indices. We've got to create the buffer out of that. And the data type is the same as for vertex buffer. It's a buffer. So we create that. We need a buffer description. The description is going to be different. Specifically, we're going to bind it as an index buffer. The other stuff is basically just the same. And that's going to look like this. And now we've just got to bind to the pipeline, which is, again, similar to this. I should probably put this after here. We'll just reorganize this for a second. Cut that out, paste it like that. And now we need to bind the index buffer. And that's done with set index buffer. And we're probably going to need some other stuff here. So pointer to index buffer. Format. Okay, so you don't bind multiple index buffers like you do vertex buffers, it seems. So this is going to be simpler, but what is this DXGI format bullcrap? Let's take a look. I guess it's one of these bad boys in here. So the format is going to be, we want 16-bit unsigned int. So I guess that's going to be this guy right here. So let's copy that. We want to bind p index buffer dot get. Good. Then our format is going to be R16 and the offset is going to be 0. And I believe that is all she wrote. And now we just got to fill in the blanks here. So index count is going to be std size of indices. And what's next? The start location is going to be 0 and the base in our vertex buffer is also going to be 0. And there you go. We are drawing index now to see if I didn't mess anything up, especially these actual indices. All right, create buffer, dimensions are invalid, byte width cannot be 0. And where is this? Line 169. All right, so you hate me because the byte width cannot be 0. Size of indices. Good old copy pasta monster. It has struck again. Change this. Didn't change this. So that's gonna be a problem, and we might as well change this one as well. That'll save us some issues in the future. Save us some tissues as well. And there you go. We've got it. And it looks like my indices themselves were right on the first try. Just a little copy pasta that got me. So yeah, that's how you do index drawing in Direct3D. And if you're not clear on the concept of index drawing in general, you can go back to my 3D fundamentals. I cover it in some detail near the beginning of that series. All right, the last thing I want to play with here for a couple minutes is the viewport. So let's try some different settings for the viewport and see what happens. We're going to set the width and the height to half of our entire window. And we're going to put the top left, we'll keep it at 0, 0 for now. And let's see what happens. What you're going to see here is you get your same scene, but it is drawn in only 1/4 of the window. So the actual scene itself doesn't change, but it's scaling onto the final destination. What you're going to see here is you get the exact same scene. It's just been scaled down now to fit within the viewport that we've specified here. And that's very useful. I mean, you could use this for many things. For example, split screen gaming, left and right, or top or bottom, or maybe you got an HUD on the right hand side. You could render to that separately from rendering to the actual main game place. And this viewport stuff, it also does clipping for us. So if we, well, let's get two birds stoned at once. Let's change the viewport position for funsies. Just to note, these are actually floating point values. You can specify floating points. I just do integers here because it's simpler and it doesn't issue any warnings, so I don't care. So now let's put one of these vertices off of the screen. So that would mean this would have to be, let's say, less than -1. And that would be outside of the rendering region. And then if we do that, now you can see here, it's getting, this part here is getting clipped. So it's actually pointing down to here, but it's getting clipped off. And the actual top left of our viewport, instead of being here, is now probably somewhere around here. All right, one last thing I want to play with to show you here before we end this video. I told you that the names of these semantics, they're free. You can name them whatever you want. So let's name this one pubes. And if I run that, you'll see it compiles and it runs, and we get a runtime error. And that is that the input signature expects position, but it doesn't get position, it gets pubes. So the problem there isn't that pubes isn't a valid semantic name. It's just that your input here has to match. So if we match this one pubes and we run it, then it works fine. So you can choose whatever names you want for these guys, except for these guys here that start with SV. Those are system values. They're specialized, and you've got to use these guys to specify very specific shader inputs and outputs. So there you go. There's a whole big grab bag of different things that you can do with this very simple pipeline setup that I've given you. And the reason why I'm showing you this is because I want you guys to be able to experiment on your own and discover all the different features and settings and just things you can do with Direct3D. You know, I don't want this to just be a checklist of me running through all the stuff you need to, you know, draw a model or whatever. I want this to be a little bit of a workshop and a little bit of a showcase on how you can, you know, explore this tool on your own. I will be guiding you, of course, as we go, but I also hope that you will be able to get some exploration in on your own with your own ingenuity and your own self-motivation. That's going to about do it for this video. In the next video, we're going to look at a more focused goal of using the Vertex shader to transform our geometry with some transformation matrices. Until then, thanks for watching. Hope you enjoyed the video. If you did, please click the like button, helps a lot. And I will see you soon with some more Hardware 3D.